Hello dear students, let us continue our discussion on linear programming. So we are in the first unit, and in the last class I had discussed about linear dependence, independence of vectors, right? And these will be necessary for our further discussion on basic solution. Okay, so today we'll discuss the topic basic solution of a system of linear equations. Okay. So before going to the main part, let me just give you one example. You had already done these things in the earlier semesters. How do I solve this equation? Suppose x plus y plus 2z equal to 3, twice x plus 3y minus z equal to 4. Okay, then suppose 3x plus 4y plus z equal to 7. Okay, so in order to solve this equation, what we do is we write it in matrix form. Okay, if you remember, we write it this way: 1 1 2 2 3 minus 1 3 4 1 multiplied with xyz. This is equal to 3 4 7. Okay, this is the system, and then we apply elementary transformations. Okay, so say second row, in order to convert this coefficient matrix to echelon form. Okay, this is echelon form. Okay, so here we write R2 changes to R2 minus say 2R1. Okay, and R3 we can change it to R3 minus 3R1. Okay, so we get 1 1 2 into xyz. So we have to apply the operations on both sides. Okay, so here it's 0, 3 minus 2 into 1 is 1, minus 1 minus 2 into 1 is minus minus 5, and here it's 3 R3 minus 3 into R1 is 0 1, and again it's minus 5, and here it's 4 minus 2 into, so it's minus 2, 7 minus 3 into this, so it's again minus 2. And the last one I can just do it this way: R3, you see the third row and the second row are equal, so R3 changes to R3 minus R2. You can do it this way. So it's 1 1 2 0 1 minus 5, and it's 0 0 0 multiplied with xyz. This is equal to 3 minus 2 0. Okay, so once we get the echelon form, here we compare that what is the rank of this part and what is the rank of this total part, means in augmented matrix. Okay, this is the coefficient matrix. Together with that, if I include this column, we get what is called augmented matrix. So here the rank of this part is 2, and rank of the augmented matrix, that is also 2, because here we have 0. If we have something non-zero here, then the rank of augmented matrix will be 3. So in that case we will not have any solution. So the necessary and sufficient condition for solution of a linear system of equation, for the existence of solution of a linear system of equation, is rank of the coefficient matrix should be equal to the rank of the augmented matrix, right? This two should be equal. Only then the system of equation will have a solution. Okay, and what are the types of solutions? Either we have unique solution or infinitely many solution. Okay, these are the two possibilities: infinitely many solutions. Okay, so if we have a unique solution, right, then we can means there is only one set of values of x, y and z satisfy the particular equation. Okay, and for infinitely many solution, okay, there are infinitely many sets of x, y, z which satisfy all these equations. Okay, but here you see, if the rank of the coefficient matrix is less than the number of equations. Okay, so here you see the third equation ultimately reduces to 0. So actually the third equation here is redundant. Okay, so if it happens that the rank of the matrix is greater than the the rank of the matrix is less than the number of these equations, okay, then actually the remaining equations are redundant. Okay, means they are not necessary. Okay, so here if you observe carefully, you see the third equation is the sum of the first two equation. Okay, so this equation does not give does not contribute anything extra to the solution. Okay, means it doesn't matter whether this equation is there or not. Okay, so that's this equation is redundant. So if we have a redundant, yeah, if we have a system where the number of equations is actually more than the number of variables, okay, then number of variables or unknowns, then always some equations here will be redundant. Okay, so we can reduce it to a system of only less number of equations. Okay, so here for example, in order to solve this whole system of equation, it is just sufficient to solve these two equations. Okay, we can just reject this third equation. Okay, because it's repeated or redundant. Okay, right. In general, if the rank is in general, if m is less than n. Okay, so let us take the general case. Let ax equal to b. Okay, be a system of m linear equations, in n unknowns. Okay, n unknowns, right. So if then it has a solution, then the system has a solution. If and only if the rank of A is equal to the rank of the augmented matrix. Okay, this is the rank of the augmented matrix, equal to R, say. Okay, let us take this as R, right. So observe that this R, what is the rank of A, this is always less than or equal to minimum of m comma n. Okay, if we have a 2 by 5 matrix, its rank cannot be more than 2. Okay, rank is always at most equal to the minimum of this number of columns and number of rows. Okay, if you have a 4 by 3 matrix, the maximum possible rank for this matrix is 3. Okay, it cannot be 4 rank matrix, right. So this is these are from matrix theory itself. So observe that the rank here is always less than or equal to minimum of m and n. Okay, so if m is greater than n, then this the number of equations is more than n, then the rank is exactly always less than strictly less than m. Okay, then this R is strictly less than m, because strictly less than m, since R is less than or equal to minimum of m and n. Okay, so R is less than m also, R is less than m also, R is less than n also, R is less than m also. Okay, so if m is greater than n, then R is strictly less than m. Okay, we can write it this way, because R will be less than or equal to n. Okay, so but n is already less than m. Okay, so R is strictly less than m. So the m minus R equations are redundant. Okay, only the first R rows will be non-zero rows. Okay, the remaining will be 0 rows. Okay, because if you have a matrix, of say size 5 row, say 3 columns. Okay, so something like this, 1 2 3 4 or yeah. Okay, so the next row will be 0 1 or 0 3 5 for the echelon form. So at most it can have say 3 non-zero rows. Okay, after that every other row will be actually 0 rows. Okay, because the rank is the maximum value of rank can be the maximum the minimum of 5 and 3. Okay, so this matrix cannot have rank 4. So what happens, but there are 5 rows here, so we are sure that after the third row every other row has to be 0. Okay, so this is what I have written. So m minus so every other row is 0 means what, we can neglect the remaining equations. Okay, so only the first r equations are necessary. Okay, the remaining equations are just redundant. Okay, this is what I have written. So m minus r equations are redundant. Okay, and we can just consider r equations for solution. Okay, equations for solution. Okay, in order to solve the problems we can just consider r equations. Okay, so so in our LPP what we will do, we will always consider m less than or equal to n. Okay, or at least for this basic solution part, m is less than n. Okay, number of equations is less than the number of unknowns. Okay, that way we will define the standard. Okay, and then see what are the basic solutions, right? So if m is greater than n, ultimately the system can be reduced to a form where the number of equations is less than the number of unknowns. Okay. Now if the rank is, if rank of A equal to rank of AB equal to R, which is strictly less than n, then R strictly less than n, then the system has infinitely many solutions. Okay. If the rank is strictly less than the number of unknowns, then the system has infinitely many solutions. Okay, and if rank of A is equal to rank of A colon B, that is augmented matrix, equal to R, which is also equal to the number of unknowns, then the system has unique solution. Okay, only one solution in this case, unique solution, right? Okay, so so for the case when m is equal to n, there is a chance that the system will have only unique solution. Okay, or it may have infinite solution. Okay, so for the only for the case m equal to n, there is a possibility that the solution will be unique, and for m less than n, the unique solution is never possible. Okay, so for m less than, strictly less than n, the system can never have unique solutions. System can never have unique solutions. Right, for m less than n, the system can never have unique solution. Okay, why? Because the rank is always less than or equal to m, and m is strictly less than n. Okay, so for unique solution, this rank has to be equal to the number of unknowns. Okay, so if the number of equations is strictly less than the number of unknowns, there is no chance that the system will have unique solution. Okay, right? So yeah, so if suppose you have, if m equal to n and rank is also equal to n, then this coefficient matrix A is non-singular. Okay. So this also follows from matrix theory. If the determinant of A is non-zero, then the rank of this matrix is equal to the number of rows or columns. Okay, it's true for singular matrix. The square matrices. Okay. So if m equal to n and r is also equal to n, then A is actually non-singular. Okay, r is equal to n, rank is also equal to the number of this, then A is non-singular, and the unique solution is given by x equal to A inverse B, right? Okay, we have done these things in your higher secondary also, and so solve the system of equation. Okay, so something was given, so you had to check whether determinant is 0 or non-zero or not. If the determinant is non-zero, immediately you find out the inverse. Okay, and then write that the solution is x equal to A inverse B. Okay, so if for the case when m equal to n, this is possible. Okay, but for m less than n, the coefficient matrix means it cannot be non-singular, because it's actually a rectangular matrix. Okay, so we cannot talk about non-singular coefficient matrix, but can we find a submatrix of A for which the solution is given by this type of expression, A inverse B? Okay, so that is basically the starting point of basic solution. Okay, so for the case when the number of equations is strictly less than the number of unknowns, okay, can we find a set of solutions where the solution basically looks like this? Okay, x equal to B inverse B. Okay, means can we find a submatrix out of A such that the solution can be written in this form? Okay, that solution is called a basic solution. Okay, right. So let us define it formally. Basic solution. Okay. Let Ax equal to B be a system of m linear equations in n unknowns. Okay, n unknowns. Where this we are considering m is strictly less than n. Okay, let rank of A, or let me write it this way, let the system be consistent. Let the system be consistent means it has a solution. Okay, let the system be consistent, and not only consistent, its rank of A equal to rank of the augmented matrix is equal to m. Okay, so we are taking that the rank is exactly equal to m. Okay, our intention is that I want to find an m by m matrix, submatrix from the coefficient matrix, such that I can write the solution in this form. Okay, so is it possible or not? Let the system be consistent and rank of A equal to rank of AB equal to m. If we can choose an m by m submatrix of capital A such that m by m submatrix of capital A, and set the n minus m variables not associated with that submatrix. Okay, not associated with that submatrix to 0. Okay, so and if we can choose an m by m submatrix of A and set the n minus m variables not associated with that submatrix to 0, then the solution that we get is called a basic solution. Okay, basic solution of the given system. Okay, of the given system. right? If we can choose an m by m submatrix of A and we set the n minus m variables, or choose the n minus m variables not associated with that submatrix to 0, okay, then the solution that we get is called a basic solution of the given system. Okay, so it's not necessary that every this system of equation will have a basic solution. Okay, it's not necessary. There may be some system where you cannot find a basic solution. Okay, so we will see some examples, right? Unless we do the examples, it's not clear. Okay, so why we have taken rank A equal to rank AB equal to m only? Okay, why not less than m? Okay, so if the rank is less than m, then we can never find m by n submatrix of A. Okay, because the rank of A, if it is less than, what is rank? Another definition of rank is the order of the highest order non-vanishing minor of A. Okay, so if rank is less than m, that means what? Every minor of order m by m vanishes. Okay, so we can never find a non-singular. If we can choose a not only m by n submatrix, if we can choose a m by n non-singular submatrix. Okay, I have to add this here. This is very important actually. M by n non-singular submatrix. Okay, please correct this. If we can choose a m by m non-singular submatrix. Okay, this is important. Submatrix. Right. Yeah. Sorry for the mistake. This was, if we can choose a m by m non-singular submatrix of A and set the n minus m variables not associated with that submatrix to 0, then the solution thus obtained, or the solution that we get, is called a basic solution of the given system. Okay, right? Okay, so for example, let us try one. Say for example, say x1, or say x plus twice y plus 3z equal to 1, x minus twice y minus 3z equal to 2. Okay, so let us see this system of equation. Okay, so what is the matrix A here? A is the coefficient matrix 1 1 2 minus 2 3 minus 3. Okay, so in the earlier definition, you see there are some words which I have used. For example, this one, n minus m variables not associated with that submatrix. Okay, what do you mean by that? So what are the vectors associated with the variable x? Okay, vector associated with the variable x is this, the first column 1 1. Vector associated with variable y is 2 minus 2 minus 2, right? Vector associated with variable z is 3 minus 3, right? That is the meaning of vector associated with the variables. Okay, that means you collect all the coefficients of that particular variable. The column vector that you get is the vector associated with that variable. Okay, right? So here you see this coefficient matrix is a 2 by 3 matrix. So it satisfies our first criteria that 2 is less than 3. Okay, m should be less than 3. So we have to look for a 2 by 2 submatrix, non-singular submatrix. Okay, non-singular submatrix. This is what we have to search. Okay, can we get such a 2 by 2 non-singular submatrix? Okay, if we get such a submatrix, then we will equate the other variables to 0, and then we can obtain a solution of this system. Okay, so here you see, so how many submatrix can you choose? 2 by 2 submatrix. So in order to choose 2 by 2 submatrix, what you need to do is you just choose 2 columns, right? So in how many ways can you choose 2 columns from 3 columns? Okay, so that's a very simple combinatorics problem we have done in higher secondary. So there are 3 columns here. in order to form a 2 by 2 matrix, what I have to do, I have to choose 2 columns out of these 3 columns. That can be done in 3C2 ways. Okay, or it's written this way, 3 ways. 3 choose 2. Okay, so that is actually 3. So there are 3 options available for us. Okay, so let B1 equal to, or say let us write it this way, B12 means I am taking first column and second column. Okay, so B12, let us write it this way, 1 2 2 minus 2. Okay, then what is I am taking first column with third column. Okay, so 1 1 3 minus 3, and then I am taking the second column with third column. Okay, so it's 2 3 minus 2 minus 3. Okay, next what I have to do, I have to check whether, so these are the all possible 2 by 2 submatrices. Okay, now I have to check whether these are non-singular or not. So I have to find out the determinant. Determinant of B12 is actually minus 2 minus 2. So this is minus 4, which is non-zero. Okay, that means B12, this particular submatrix, will correspond to a basic solution. Okay, then determinant of B13, that is what, minus 3 minus 3. So that is minus 6, which is non-zero. So if I collect first column and third column, then also I will get a basic solution. And what is determinant of B23? It is actually minus 6 plus 6, so that is 0. So it's singular. So 2 3 doesn't give me any basic solution. Okay, so how B12 will give us basic solution? Let us see. So let us write this equation once again. X plus twice y plus 3z equal to 1. Okay, and x minus twice y minus 3z, x minus twice y minus 3z equal to 3. Okay, this is the system. We have seen that B12, determinant of B12 is non-zero. Okay, so B12 inverse exists. Okay, B12 is an invertible matrix. Okay, so what we can do is we can putting z equal to 0. Okay, so the first 2 columns they will give us the basic solution. So as per the definition, you see what is the definition. If we can choose a m by m singular non-singular submatrix of A and set the n minus m variables not associated with that submatrix to 0, then the solution that we get is a basic solution. Okay, so here you see what are the variables associated with the submatrix? Only x and y. These are the variables associated with this first submatrix. So z is a variable which is not associated with this submatrix. Okay, so we will put z equal to 0. So putting z equal to 0, we get, so we'll write it in a matrix form, 1 2 1 minus 2 of x y equal to 1 3. Okay, this one. So z is already 0. We have reduced this system of 2 equations in 3 unknowns to a system of 2 equations in 2 unknowns. Okay, where means the reduced system has a unique solution because B12 is invertible. Okay, so we get this equal to 0. So this implies xy is actually equal to this 1 2 1 minus 2 inverse multiplied with 1 3. Okay, so we have to find the inverse of this matrix. Okay, so what is the inverse of this matrix? So the inverse you can easily calculate. It's 1 divided by determinant. Okay, what is the determinant? Determinant is minus 4. Okay, and we have to find out the adjoint of this matrix. Okay, adjoint is the transpose of the cofactor matrix. So what is the cofactor of 1 here? Cofactor of 1 is minus 2. Okay, cofactor of 2 is actually minus 1. Okay, if you just remove this and this first row and second column, okay, then you get here minus 1. So cofactor of this is minus 1, and again cofactor of 1 here will be minus 2. Okay, so cofactor of 1 will be minus 2, and cofactor of minus 2 is again 1, and then we need to take transpose of this matrix in multiplied with 1 3. Okay, so ultimately it's 1 4 multiplied with minus 2 and minus 1 1 multiplied with 1 3. Okay, so what is that? If you simplify, this is minus 2 minus 6, that is minus 10. Okay, and minus 1 plus 3, that is 2. Okay, so it's ultimately the solution that we get is x equal to minus 10 by 4 minus 5 by 2, y equal to 1 by 2, and z equal to 0. Okay, so this is a basic solution. Of course, this system has infinitely many solutions or not. Let us just check whether it has infinitely many solutions or not. Here it has only this is, if we 1 2 3 1 minus 2 minus 3. Okay, so if we just subtract 1 2 3 0 minus 4 minus 6. Okay, so here rank is 2, which is equal to the number of which is less than the number of unknowns. Okay, so here also the system will have infinitely many solutions. Okay, so that already I had pointed out. If number of equations is strictly less than the number of unknowns, then there is no other option. There are infinitely many solutions. Okay, but out of those solutions, this is called basic solution. Okay, because the vectors corresponding to this basic variables, okay, are or form a non-singular matrix. Okay, so I hope you understood this part, and let us find out another basic solution which corresponds to so the submatrix B13, I think. B13 also gives a basic solution. Okay, gives a basic solution. Okay. So what was that? X plus twice y plus 3z equal to 1, x minus twice y minus 3z equal to 3. Okay, so we have seen that determinant of B13, this is non-zero. So we will put or we will equate other variables to 0. So variables which are not associated with this submatrix. So this submatrix is formed only by first column and third column. So the variable that is not associated with the submatrix is the variable y. So we put y equal to 0. Okay, so we putting y equal to 0, we get x plus 3z equal to 1, x minus 3z equal to 3. Okay, so we will solve it. Solving, we get 1 3 1 minus 3 of xz, this is equal to 1 3. Okay, so you solve it very easily. Xz is actually equal to 1 3 1 1 minus 3 inverse multiplied with 1 by 3 1 3. Okay, so we have to find out the inverse of this. So it's 1 divided by determinant of this, minus 3 minus 3 minus 6, and then just find out the cofactors. Cofactor of 3 is minus 1, so let me write it here, minus 1, so I don't need to take transpose again. Minus 1 means I have already taken transpose. Okay, so this is what I have to write. This is minus 3. Okay, multiplied with 1 3. Okay, so your solution is 1 by minus 6, 1 minus 9 is minus 8, minus 1 minus 9 is minus 10. Okay, so this is given by 4 by 3, and this is given by 5 by 3. Okay, so another basic solution is x equal to 4 by 3, y equal to 0, and z equal to 5 by 3. Okay, this is one more basic solution of this system. Okay, right. So out of the given m columns or n columns, I have to select m columns. Okay, so in how many ways that can be done, and for each selection I have to compute the determinant of the corresponding submatrix. Okay, for each selection I have to compute the determinant of the corresponding submatrix. If the determinant is non-zero, then that particular submatrix will correspond to a basic solution. Okay, then we can find it out by equating other variables to 0. Okay, we equate all other variables to 0, then we can find it out. Okay, so so the variables which correspond to this basic thing, a basic solution has not more than m non-zero variables termed as basic variables. Okay, So as a continuation, we can just write this part. What are basic variables? Okay. Right. Basic variables. Okay. So let Ax equal to B be a system of m linear equations in n unknowns okay, where m is strictly less than n. Okay. Also let rank of A is equal to rank of AB equal to m. Okay. So if we can choose an m by m non-singular submatrix of A and set, if you can choose and set the n minus m variables not associated with this submatrix to 0. Okay. Then the corresponding solution that we get is called basic solution, and the variables, the m variables, okay, and the m variables associated with the so let me just write it. If we can choose an m by n non-singular submatrix B of A such that and set n minus m variables not associated with this submatrix to 0, then the corresponding solution that we get is called a basic solution, and the m variables associated with the submatrix B are called basic variables. Okay. B are called basic variables. Okay, so for in the example that we had done, suppose here what are the basic variables? X and Z, they are the basic variable. Y is a non-basic variable. Okay, in the earlier example, X and Y, they are basic variables. Z is a non-basic variable. Okay, right? So that is the definition of basic variables. Okay, then the matrix formed by the coefficients of the basic variables, non-singular. So thus the vectors associated with the basic variables, okay, are thus the vectors associated with the basic variables are linearly independent. Okay, linearly independent. Because in the earlier class we had seen, if the determinant of a matrix is of a square matrix is non-zero, then the column vectors as well as the row vectors, they are linearly independent. Okay, so the vectors associated with the basic variables are linearly independent. Okay, right. So we can also say that what is the basic solution of a system Ax equal to b. So a solution will be called basic if the vectors associated with m variables are linearly independent, and the remaining n minus m variables are all zero. And then we say that the solution is a basic solution. Okay. So right, so let us write that part also. Okay, thus the vectors associated with the basic variables are linearly independent. To find a basic solution, we are first to select m linearly independent. Yeah, so let me write this as a note. Thus, to find a basic solution, we need to find m vectors, that is column vectors. Okay, column vectors in the coefficient matrix. Okay, in the coefficient matrix which are linearly independent. Okay, which are linearly independent, and we have to set the variables associated with the remaining vectors. Okay, associated with the remaining vectors, remaining how many are there? Remaining n minus m vectors to 0. Okay, this is the procedure. We select m vectors which are linearly independent. The easiest way to do that is find out the matrix determinant of the corresponding matrix. Okay, so we need to find m column vectors in the coefficient matrix which are linearly independent and set the variables associated with the remaining n minus m vectors to 0. Okay, so thus in a basic solution, of Ax equal to b, where of the system Ax equal to b of m equations in n unknowns. Okay, m equations in n unknowns, okay, where m is less than n. The number of non-zero variables, we have already set n minus m variables to 0. Okay, so what is the maximum number of non-zero variables? Total there are n variables, and we have already set n minus m variables to 0. Okay, so what is the maximum number of non-zero variables? What can be the maximum number of non-zero variables? Okay, it's actually m. Out of n, we have set n minus m to 0. We are sure that remaining n minus m are 0. So number of non-zero variables is at most, okay, hence it cannot exceed, right, is at most m. Okay, there cannot be more than m non-zero variables. Okay, right, this is the thing. Okay, right. Okay, so how many so if the maximum number of basic solutions will be what? See, I told you that we just have to select m columns out of n columns, okay, and then test the determinant of each of these. Okay, that is the procedure. This is the procedure. To find a basic solution, we need to find m column vectors in the coefficient matrix, okay, which are linearly independent. So we have to find m out of n. Okay, so how many ways can we find that? The maximum number of basic solutions will be n choose m, okay, and that is ncm. Okay, so that is factorial n divided by factorial n minus m into factorial m. Okay, so this is the maximum number of basic solutions. Okay, so if we are given a system having 3 equations with 7 unknowns, the maximum number of basic solution will be 7c3. Okay, so that is factorial 7 by factorial 4 into factorial 3, whatever it is, that is the answer. Okay, maximum number of basic solutions, right? Okay, then we have some problems. We will do it, right? Okay, let us try another one. Say find all basic solutions of, okay, say x minus y plus 2z plus t equal to 1. Okay, another one is twice x minus twice y plus z, or say plus twice z minus or plus twice t. Okay, twice z plus twice t, or twice z plus t, okay, equal to 3, right? So let us try to find out all basic solutions. Okay. So here the coefficient matrix is A equal to 1 2 minus 1 2 minus 1 minus 2, then this is 2 2 and 1 1. Okay, this is the coefficient matrix. So maximum number of basic solutions will be, so there are 4 columns. Out of 4 columns we have to select 2 at a time, okay, because the number of equations is only 2. So 4c2, that is 6. So we have to check 6 submatrices. Okay, so we will do it logically so that we don't mess up. Okay, so B12, we consider the 6 submatrices of order 2 by 2. Okay, 2 by 2. So what is that? B. So first I'll consider B12. Okay, first row, second column. Sorry, first 2 columns. Okay, 1 2 minus 1 minus 2. Okay. So determinant of B12, what is that? Determinant of this is minus 2 plus 2, that is 0. Okay, so B12 doesn't correspond to basic solution. Okay, it doesn't correspond to basic solution. Okay, then we will check B13. Okay, let us go serially. B13, determinant of B13, what is that? Determinant of B13 is 1 2 2 2. Okay, 1 2 2 2. Okay, so this determinant is 2 minus 4, that is minus 2, which is non-zero. So therefore B13 corresponds to basic solution. Okay, corresponds to a basic solution. Okay, so we will find it out. How to find it out? B13. Okay, I said B13, right? Yeah. So B13 means first column and third column. So in terms of vector, what are the corresponding vectors? For the first column I have the vector x. For the third column I have the vector z. Okay, so this x and z are the basic variables now. Okay, so we will put the remaining variables to 0. We will set remaining variables to 0. Okay, so so here B13 corresponds to a basic solution with x and z as basic variables. Okay, so you can write that part also. X and z as basic variables. Okay, so putting y equal to t equal to 0. Okay, so other variables we put 0 so that it's easier to compute here. So putting y equal to t equal to 0, we get, so what do you get? X twice x, and so we can write it from here itself, from the matrix itself. We get 1 2 2 2 multiplied with x z equal to what was the right hand side? Right hand side 1 3. Okay, 1 3. So this implies x z equal to, so we have already checked the determinant, so its inverse will exist 1 2 2 2 whole inverse multiplied with 1 3. Okay, so if you find out the inverse, it's 1 divided by, determinant is 2 minus 4 is minus 2. Okay, and this here will be this 1 will be 2, and the cofactor for this 2 is actually minus 2, so it will go here. Cofactor for this 2 also is minus 2, so it will come here. Cofactor of 2 is 1. Okay, so it's 1 1 3. Okay, so we just multiply this 2. So half 2 minus 6, so that is minus 4, minus 2 plus 3, that is 1. Okay, so it's minus 2 comma half. Okay, so basic solution is x equal to minus 2, y equal to 0, z equal to half, and t equal to 0. Okay, so this is a basic solution of this given system. Okay, so other basic solutions also you try to find out. B14, okay, see whether it is basic solution or not. Then B23, okay, whether it's a basic solution or not. Then also check B34 whether it's basic or not. Okay, so these things you please check and complete it at home. Okay, so next class we will discuss some more about it. Right, thank you.